Hello again, this is Bruce Wallenberg. This is lecture 12A. This is the first of two lectures on optimal power flow. What we're going to do is we're going to start out and talk about economic dispatch, which of course we've covered in detail in earlier lectures, there being a very large chapter on that topic in the book, but it's necessary because economic dispatch plays a big role in the optimal power flow. So let's go back again and remember that the objective function of economic dispatch and for optimal power flow is to minimize the sum of the operating costs of all the generators that are online, that are in the model. The generators have their standard minimum, maximum limits, one for each generator, and the total load plus total losses minus the sum of all the generation is equal to 0. Now this is the summary of the economic dispatch. Okay, that's economic dispatch. Now, what I'm going to do is I'm going to combine economic dispatch and power flow. I'm going to combine the two. The objective function, well, minimize total cost, just the same as in economic dispatch. Generator limits, same as in economic dispatch. There's no difference there. However, for each bus, now you notice that we don't start talking about the total load and the total losses and the sum of the generation. We're not going there anymore. We're going to go down and immediately go to the power flow. So the P-gen minus P-load must equal the net power flow at each bus. So I should put an I here. I should put this is the conditions at each bus. I use the Y matrix power flow equation for the bus, introduces the voltage, magnitude, and phase angle for each bus, not including the reference bus, into the problem. So I have now just added 2 times n bus minus 1 equality constraints. That's this equation up here. You have one for every bus except for the reference bus, and of course it's complex, so there's really a P and there's a Q equation. So we can see here on the next page. So here's the OPF problem stated mathematically. There's the objective function. Once again, minimize the sum over all the generators of the operating cost. There is the generator limits, the inequality constraints for generators, and here's the inequality constraints on generator reactive power. Now this equation here is in complex numbers. So it says that the P net plus Q net at every bus is equal to VI conjugate. This is just this term in here is I sub I. It's the net current. So this is just basically the power flow. And of course we have the conjugate right up here. We have a star for the conjugate. So this equation up here gets broken into two equations like this. The P gen minus P load minus the real part of the VI conjugate equation. The Q gen minus Q load minus the imaginary part of that same equation. So there's two. We break that complex set of equations into sets of 2 for each bus, 2 real equations for each bus. Now, let me just back up one second. This is what I've reviewed here is a very, very complex problem. It's a very complex problem to solve this. The original papers were done by a Frenchman named Jacques Carpentier. I met him on a couple of different occasions when I was younger. He was an engineer that worked for the French power company called Électricité de France, and he was a real gentleman. Met him at conference in France once, and he also came to my place of work where I worked in Schenectady, New York at one time. He started work on this very, very early. I'm going to say back in the 1960s, and it literally took about 30 years before many, many people working on the problem had worked their way through the many different techniques till we had good, reliable, solidly reliable techniques to solve the optimal power flow. It took a long time. It took a long time to get good, solid solutions. We'll talk about them later. But the solution of the optimal power flow later on in the 1990s and 2000s became the basis of the transmission operations for the modern power markets. Without those optimal power flow solutions, the modern markets would not have been able to operate. Okay, the results. This is the part that I like about the OPF. Generator outputs, the sum, I should say, of the generator outputs equal the load plus the losses. When we did that as an economic dispatch, the losses were not necessarily a function. Now, earlier people had come up with approximate functions, the so-called B matrix equations and so forth. But in truth, the only way to really get the economic dispatch to balance with the power flow is solve the economic dispatch, put the generations into the power flow, solve the power flow, calculate the losses, go back to the economic dispatch, iterating back and forth, and it would converge. But the OPF does that all at once. So the losses are inherent in the power flow itself. So there's no need to explicitly calculate them. We can include the generator megawatt and megavar limits right in the calculation. So the megavar limits are also there. We can include, now this is where we can really go places we couldn't before, transmission line or transformer limits on either megawatt or MVA flows can be included into that. So we're saying I can get a minimum cost solution with a balanced power flow. Oh, and by the way, I can make sure that none of these lines are overloaded. We can include bus voltage limits so that I can be sure that I don't dispatch the system and have a very low voltage at some place in the system. Later on, near the end of the second lecture, we're going to show you how to do limits on what we call security constrained OPF, which is adds another level of complexity to the problem. So the OPF really solves a lot of problems in one calculation, and we're going to go through how we do that. The first thing we're going to do is I'm going to set it up using the linear power flow. Now, you're going to say, wait a minute, this is, now you're really simplifying. Yes, I'm simplifying it in order to use it as a teaching tool here, but we will get back to solutions of the OPF for AC later on in the lectures. Okay, so we're going to use the DC or the linear method up here, DC or linear power flow. Once again, we have the same minimize the sum of the operating expenses, generation limits, and now I have one set of linear equations. These are vectors of generation vectors. These are as long as the buses. And so this is the equation here, B sub x matrix times a vector of phase angles in radians. B sub x is in per unit. Now that means that this equation, if B sub x is in per unit and these are in per unit, then we have to change something because we like to keep the rest of the economic dispatch items in megawatts. So I'm simply going to go in here and multiply by 100. That says that these are now megawatts. So these two quantities are now megawatts. This is still radians. This is in per unit, but 100 times it makes this whole thing balance out. So there's my Lagrangian. It's the sum of the operating costs plus lambda transpose. Now that's a vector times every bus in the system. This matrix has got the number of buses. So this is a vector that's got one lambda for every bus. This is very, very significant. So let me just say this. There's one lambda per bus. So just keep that in mind. One lambda per bus, and that's going to be very significant later on. So now we have these. Let's say I have a network with 500 buses. Then I have 500 equations here and 500 lambdas. I add one more lambda because I have a constraint, and it's best, I believe, to solve this this way. The reference bus phase angle has to be kept at 0, and so I add one more constraint, this lambda NB plus 1. And if I want to put up other constraints in, such as the generation has to be between the min and max, well, then I have another set of Lagrange multipliers called mu, which, if you remember from our discussion of the KKT conditions and so forth, mu is either 0 or it has a value that tells us whether, the value of that constraint's being held. These are inequality constraints on the generator limits. Now, I haven't had anything to do with transmission limits yet, but we will. Here's an example. Here's this is the one in the book. Here's my three equations up here for the cost of operating the generators. Here's their limits. So I have 600 plus 400 plus 200. I have 1,200 megawatts, and I'm going to solve this, and I'm going to solve it for 850 megawatts of power. We look down here, and it should be. Yes, it's 800. Yeah, 850. Okay, so we set it up when we solved it for 850. Well, now I'm going to go and I'm going to do this. I'm going to say, well, here's the 850. There's 200 here. There's 550 over here. That's 750, and there's 100 down here. So there's. Now that 850 is going to be located at 3 different buses. Okay, here's the 200, 500, and 100, and I'm going to give you the X, the susceptance for each transmission line, and we're going to then formulate the OPF problem with 3 transmission lines. So here are the X's for the transmission lines. This comes right out of the book. And we build the B sub X matrix. Remember, this is the equation for that matrix. It's 1 over x12 plus 1 over x13 minus 1 over x12 minus, etc. It's a symmetric matrix, so the same term appears above and below. This is our standard formula for calculating this B sub X matrix. And then when we multiply it by 100, we get this matrix down here. So this is the one that I'm going to use, and it's just the B sub X matrix multiplied by 100. So I'm going to formulate my Lagrangian. I'm going to add the sum of all of the cost functions. This is bus 1. Okay, I will write this out. Bus 1. This is bus 1 right here. Here's bus 2 and here's bus 3. So you'll notice that what this is it's lambda 1, and this is the first row of that matrix times the P-gen at 1 minus the P-gen plus the P-load. Well, really it says these three equal the P-gen minus the P-load, but I brought those over to the other side. So this, what's inside the brackets has got to add up to 0, and then you multiply it by the Lagrangian. So I have three buses, pardon me, and so I have 3 lambdas here, 1 per bus, plus I have this fourth one to keep my phase angle equal to 0 at the reference bus. So now look at the problem variable. The original economic dispatch had P-gen 1, P-gen 2, and P-gen 3, and it would have 1 lambda. It would have 4 variables. Well, now we have the 3 generators, and I have 3 phase angles, 3 lambdas, 4 lambdas. So I've suddenly really increased the size of the problem, but it's a more complex problem. It's going to give us more information. So here it is. You have the solution. You start taking the derivative of the Lagrangian with respect to each generation. There it is there. The derivative with respect to each phase angle, right there. The derivative with respect to the 4 lambda variables are there. And so we have 10 variables and we have 10 equations to solve them, and they're all linear equations. Now, let me back up just a minute. I ignored the P-gen limits in this problem. I did that purposely so that we could set it up. So this problem does not solve with the limits. It ignores the limits and it just reaches a solution. And you're probably thinking, and probably very correctly, that Wallenberg loaded the solution up so that they wouldn't come out outside of their limits, and that's correct. So I did it that way. We'll get back to those generator limits. They're very important, and we will put them in the problem later. But I wanted you to understand how these things work about. Where did all these lambdas come from, and what good are they at the end? Okay, so here's my set of 10 variables, 3 generators, 3 lambdas, 3 phase angles. Here's the 3 generators, the 3 phase angles, and the 4 lambdas. And there's 10 equations, 10 unknowns, and there's the numeric one right there. And I just put that into a MATLAB program and said, give me the solution. And there's my solution. It gave me these 3 generator variables that are in limit. And it turns out that this is a very significant conclusion, that the lambdas are all equal. I'm going to talk about that in a minute. Here's the phase angles, and from this I can. So here's one of the outputs of the power flow of the OPF. I can tell you what the power flow is along each transmission line. That's built into my solution. So remember now, the OPF solves the economic dispatch, and it solves the power flow all at once, simultaneously. Let's get back to these lambda values. The lambda values are all equal. In this case, they're all equal because there are no limits being placed on the transmission lines. There are no limits on the transmission lines. When we do that, we will see that the lambdas change. You should remember that lambda can be defined as, in this case, what is the increase in system operating cost if I add 1 megawatt to the load. So if I add 1 megawatt to the load at bus 1 or 2 or 3, 1 megawatt will increase the operating cost by $9.1483 per hour. That's the precise number. And it's the same everywhere. It is the same everywhere because, and in this case also because there's no losses and because there's no transmission lines at limit. We're going to see that change in a second. I'm going to now add a line flow constraint. Here it is. I'm going to say I'm going to say that the flow from 1 to 2 should be limited to 150. So that's this line here, and I don't like 158. Can I limit that flow to 150? So there's the linear power flow equation. Once more, the 100 is because this is in per unit, so I have to multiply the equation by 100. These are radians. This is megawatts here. Here's my statement of the problem again. Sum of the power flows. There's one of these per bus. There's for each bus. That's the net equation for each bus. Here's my reference bus phase angle equation, and here's my limit equation over here. And now I had to add lambda 5. So I includes one more Lagrange variable, because I've added one more constraint to the problem. When I solve that, and you solve it the same way, you take the derivative of L with respect to P gen 1, 2, and 3, with respect to the thetas, with respect to the lambda 1, 2, 3, 4, and 5. And you'll get enough equations to solve them. They're all linear equations. And when you solve them, you will get an equation where a solution where this flow is now limited to 150 megawatts. The cost is just a little bit greater than it was before, and the lambdas are no longer equal. The lambdas are no longer equal. We're going to go back and visit that issue at the end of the second lecture. We'll talk about the significance of the lambdas, or what are called the locational marginal price. But notice that this solution, the loads are the same, but I have adjusted generation so that this is now 150. The cost is a little bit more. It's not as cheap as it was the first time. Now, some practical details. Line flows, of course, are inequality. I set the last one up. I put an equality constraint, but that should have been an inequality. It should obey the Kuhn-Tucker-Karush conditions. One solution would be to formulate the OPF as an LP, as was done in ED, and add the transmission and equality constraints. We're going to solve one. We're going to show how we can do that. We're also going to show later on how we can do an AC with LP, an AC solution with LP. Another is to use quadratic programming. This is a very convenient way, because my cost functions are quadratic. My transmission constraints with the DC power flow are linear, and so I can set it up with quadratic programming, which we also have equations, or programs that you can use written using the MATLAB quadratic programming solver. So you can use quadratic programming. Here's OPF with DC power flow using LP. So if you remember in the economic dispatch chapter, we said I can break this function as you take the minimum and then you add a series of segments, where these are segments, and these are the slopes of the segments, and each segment has a limit from 0 to some max. K is the segment in let's see. Now, K is the segment index. We have 3 segments in there, and then the PI is equal to the Pmin plus the 3 segment values. So this covers my generator nonlinear function. Same linear function for for the same linear function for the loading, for one for each bus. The generation, of course, has a min and max constraints, and now we're going to put flow limits where I have the flow is less than or equal to a maximum flow. Reality says that the flow could be negative, and we're going to show you how to set up an equality constraint later on to take care of those two-sided constraints. So let's go into that right now. That we develop what we call a slack variable method for a double-sided constraint. Double-sided simply means that the flow, that's this value, we want to constrain it to be less than plus 150 and greater than minus 150. So it has to be between minus 150 and plus 150. I do this. This is a technique that I've worked on. I worked out years ago, and it's nothing earth-shaking. It just says you add a slack variable, and we say that slack variable then will make up difference, and it goes up to 150. Now, what is the value of the slack variable? The slack variable should be able to go between 0 and twice this max for the constraint over here. So in our case, it goes from 0 to 300. Okay, if the value is 0, then we know that the flow is up against the 150 constraint, because that would say this is 150 plus 0 equals this. If this is 300, that means this one is now up against the minus. This is negative 150 plus 300 equals 150. So these are not explicit constraints. These two values are the upper and lower bound on the variable S12. The upper and lower bound on the variable. You remember when we did the LP lecture, we talked about the fact that upper bounding is one of the more useful features of an LP code. The MATLAB code uses this linprog algorithm, which has upper bounding. So now let's look at the QP. Quadratic programming says that this thing, as a set of vectors, there's a set of A values times a vector of 1s, B values times, now here's our unknown vector is the vector p gen 1 through n, and then we multiply the p gen vector times this C vector, which is C matrix, which is really just a diagonal. There's the C values across here times p gen. So this is just the sum out here, just like we had before, but it's expressed in this notation with the p gen vector. Same p gen minus p load equation we had before, same inequalities on each generator. Here's my slack variable, same for the transmission line limits, and so that the quadratic programming solution will work quite well. Incidentally, even when you use linear programming, the MATLAB linprog routine will output the Lagrange multipliers that you can pick up very easily, and the code that's available on the web page that you can use with this course has that solution in it. Thank you.